Buenas noches. Buenas noches. Good evening. I think we're overdue. A Newton night. Okay, so what we have here is just the motion. Don't want to go into the whole gravitation and everything. It could be overwhelming, couldn't it? We'll do the laws of motion. So the first law of Newton's motion is this here. This 1961. This is the old way it was told, the old way it was written. Everybody continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces suppressed upon it. Now what this means, try to keep this in layman's terms. That ball will stay there until something moves it. That's the first part of the first law. Check it out, watch. It gets me every time. It's fascinating. Look, that's going to stay like that until something moves it. And then there's the opposite. Something moving will carry on moving until something stops it. Now this is a little bit, not more complicated, but because of gravity, look, and friction, look. See how it stops? So it is an external force that stopped it, isn't it? Because gravity or density and buoyancy and the friction, look. And now you go straight into the first part. That ball, I'm changing the wording, that ball will stay there until someone kicks it. That's his first part of the first law. Watch, I am now going to show you what that means. See that? Right, stand easy. Now, the second law, the change of motion is proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. Now, listen. It's not that complicated, right? Don't get scared. What that means, if this ball is traveling that way and I come along, right, and I kick it like that, what's going to happen? It's going to go, and the minute I kick it, it's going to go in the direction that I kick it. Watch. Can you believe that? Did you see that? Watch. See, that's the law. And an object or whatever will continue in a certain direction. But if something comes along and knocks it, it goes in the direction of the knock. It doesn't go the other way. It's truly compelling. So if the ball's coming towards me and I decide to kick it the opposite way, the ball is going to go that way. That is the second law. And the harder I kick it, the further it's going to go. Should we kick it really hard? We shouldn't do it because I could break stuff. But watch. Look. Boom! Now, there is also, obviously, don't let this throw you, right? It's still the same law. You can do a 90-degree angle. If the ball's coming this way, and I'm stood here, and when it gets about level with my ankle, I go like that. The ball goes, watch. But that, we were doing the second law, and then that was in the first part of the first law, where it wasn't moving. It was at rest and was going to stay at rest until something, and that something was that. We just covered the first and the second laws in one. That's what I'm talking about. Did you need to be told that? do you need to be told that that's going to stay there until something gives it a tap? It's one of the laws, you know. Did you need to be told? Oh, I look like a footballista now, don't I? So we've covered the first two laws. All afternoon, I've spent revising this to see if I could get through those two laws. I think I just scraped through. Then we have the third law. Now, it's not worded every action has an equal and opposite reaction. It's worded to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to the contrary parts. Think about this one. It says it's always going to be an equal. Anyway, that doesn't matter for now. So what we have here is every action has an equal and opposite reaction. Now, it's great to read the old school definition of a vacuum. I love it. It's really good. Well, vacuum. A space in which there is no matter, or in which the pressure is so low that any particles in the space do not affect any processes being carried out there. So, first of all, we have to ask ourselves, if Newton came up with those scorchers, I mean, there's some serious laws down there of motion, and he came up with every action has an equal and opposite reaction, 1600s, would he have been referring to a vacuum for every action has an equal and opposite reaction? 1600s vacuum. What do we think? I know what I think, but it's not about what I think. It's about logic and common sense. Do we think that in, 1666 or 1668, somewhere along there, 300 and a couple of years before it was needed? Every action has an equal and opposite reaction. In a vacuum, wasn't needed for 300 years. So would he have been, think he had that in mind when he came up? I mean, who knows what he had? Who knows what he was thinking? Just seeing the first two, it's just fascinating stuff. Vacuum, space in which there is no matter, or in which the pressure is so low that any particles in the space do not affect any processes being carried out there. We've been here before, so we have two rockets, right? They're both coming down to land on the moon, and they both bang their thrusters on, but we didn't tell the astronauts, which was a bit naughty, in this rocket that they're in a sealed glass container. We didn't tell them. They took one for the team, okay? Now, when they throw their thrusters on, they're coming down, they're in a glass container, really clean, so they don't know they're in there. And they're headed towards the moon. They're descending to the moon like the Eagle did. But they're in a jar, glass container with the lid on tight, proper tight. Right? Now, they throw the thrust on. What's going to happen? Is the glass jar going to slow down? Well, it can't really, because any thrust coming out of there cannot interact with the outside, can it? So, I think we know what's going to happen. The glass jar is going to carry on, probably speeding up, if the gravitational pull from the moon is what they say it is. It's going to be a disaster. It's not going to slow down, is it? how on earth is that rocket going to slow down if it's in a glass jar? It can't, because it cannot interact, even if every action has an equal and opposite reaction. No, it's not going to happen, is it? What about this one? This one's coming down. It's not in a glass jar. Puts the thrusters on. What do we think is going to happen? Do we think that there's going to be an upward pressure? Because every action has an equal and opposite reaction. But vacuum, space in which there is no matter, or in which the pressure is so low that any particles in the space do not affect any processes being carried out there. So basically, it too may as well be in a sealed container, because when the thrust comes out of here, the first thing it's going to do is dump into the vacuum, because it's obvious that stuff takes the path of least resistance. Doesn't matter how much pressure you build up under the thrusters or the nozzle, there is nothing for the thrust to work against to slow the rocket down. It's insane to say, yeah, but thrust, they work better in the vacuum space because they don't get clogged up, there's no resistance. It's a bit silly. If we have a motor car, right? Right? So, your argument, God, I'm a good drawer, aren't I? Eh? Your argument that these thrusters, they work better in a vacuum. It's kind of hard to argue with. I suppose they probably would, because there's no resistance. This car, do we think if we took the road away from the car, do you think the wheels are going to spin a bit better? If we jack it up. What do you reckon? How those wheels go compared to when it was on the ground? I reckon they're going to go a lot better, don't they? They won't even wear, will they? But the car's not going to get anywhere, is it? It's the same deal. Not only have they tried to bamboozle people with thrust in a vacuum, they actually go one step further and tell people that they're more efficient. It's the way they do things. Not happy with just trying to get away with it, they go the extra mile and say it's more efficient. More efficient, my ass. Thrust will not work in a vacuum because there is no resistance. Nothing can self-propel. Space in which there is no matter, or in which the pressure is so low that any particles in that space are definitely not going to affect any processes that are being carried out there. So if that car didn't move, that rocket is going to smash into it. Folks, listen. Common sense. Oh, this right here. This is the one that fascinates me the most. Who comes up with something like that? Who comes up with something? This will stay at rest until something comes along and moves it. What a law, isn't it? Did you need to be told that? Did you need to be told that if you kick the ball on the right-hand side, it will go to the left? All right, later, peeps.